So in order to illustrate properly how the magnetic potential comes about, let's maybe begin with introducing, just recording Maxwell's equations. So let's just see Maxwell's. So let's just record Maxwell's equations. So there are four of them. We have Gauss's law for electricity. That tells us that the divergence of the electric field is rho on E0, the permitted just free space. You have Gauss's law for magnetism, which tells us that the divergence of B is 0. And you also have Faraday's law of electromagnetic induction, which tells us that the curl of the electric field is negative dB dt. In other words, if you have a changing electric field, then if you have a changing magnetic field, you can get an electric field from that. And then the last one, you also have Ampere's law, which in this case tells you that if you have a changing electric field, you also have a magnetic field that can be generated from that. So the curl of B is equals to mu 0 J, so some displacement current, plus mu 0 E0 delta E delta T. Okay, so here we have the four Maxwell's equations. And now, in order to properly illustrate where the magnetic field comes about and how it's linked actually to the electric field, let's just mention a very important property. Okay, actually it's kind of a mathematical tool that would help us to understand or to derive this, and that is the Helmholtz decomposition. What this states is that if you have any vector field, say F, then this vector field, you can decompose it into two components. So a first one, that's a gradient field, I'm going to call it G, and a second one, that's a rotation field. Okay, so we can give expressions to each of these fields. So a gradient field, we can write it as in terms of a scalar field, so like negative nabla phi. You know that the nabla operator would convert any scalar quantity into a vector. So our gradient field can be represented thus. And so this is irrotational. It's a gradient field. And then another component which will account for rotation, that's a rotational field, and that has to be the curl of some quantity that we can call here A. Okay, so that being said, you'd realize that the electric field as well as the magnetic field are vector quantities, which means we can decompose each of these following the Helmholtz decomposition. Okay, so let's begin maybe with the electric field. So for the electric field, we are going to write our E as negative nabla phi plus the curl of some A. Okay, let's just call it A in this case. And let's try to see what this implies for Gauss's law of electricity. Gauss's law tells us that if I take nabla of E, so nabla dot, I'm going to substitute the expression for E here, and this has to be rho on epsilon 0. Actually, just note that this is a scalar, so it's just like some constant if you want. So constant. Okay, so if we try to simplify this, you notice that we are going to have the first will just give us negative nabla squared phi, okay? And the second is going to give us nabla dot the curl of this quantity, and this has to be some constant. Okay, so this, you probably guessed it, is just going to be 0. So this is going to be 0 because if you have the gradient operator and you take the cross product with another quantity, then this is going to be perpendicular to both the gradient operator and the quantity in question. And when you take the dot product of a field that's perpendicular to another one, you get 0. So this quantity is 0. Thus, we are left with just this, which can be written actually as negative the Laplacian of phi equals to a constant. And this works because the Laplacian of a scalar field, okay, is just a constant. So we can deduce from this that the electric potential phi, the electric potential is just a scalar field. Okay, and what this scalar field represents is just the energy, similar to a gravitational field. It's just like the energy per unit charge that will be required to move a charge from one point in an electric field to another. So this, I guess, we are used to this one. Okay, so now let's see what we get for the magnetic field. So similarly, we can also write B, using Helmholtz decomposition. So I'm going to write it as negative nabla phi plus nabla cross E. Yeah, so I'm just using the same expressions, but you get it. This phi is just like a scalar field if you want, and A is a vector field. Okay, so B is written thus. Now, what we are going to do, we are also going to replace it in the expression for Gauss's law of magnetism, which tells us that nabla, so the divergence of B has to be 0. So I'm going to plug B here. So we have this plus this equals to 0. Okay? And then if we simplify this, we're going to have, so here we're going to have negative nabla squared phi. And then here we're going to have nabla dot nabla cross A equals 0. Okay, so you realize that we have the sum of two quantities that must be equal to 0, okay, for the divergence of V to be 0. And then this first part, negative nabla squared phi, phi is just a constant, and you're kind of rubbing the spatial derivatives of a constant, second order derivatives, if you want, of a constant, and this has to be 0. So here, phi must be a constant such that the second order derivatives would just give us 0. And this would leave us with nabla dot nabla cross A, which indeed is 0. Same reasoning as we previously did. If you have the cross, the dot product between two perpendicular fields, the result is 0. So this allows us to confidently say that B can be written as the curl of some field A. Okay? And this K is what is known as the magnetic potential. And this magnetic potential is a vector field. Okay? So this is how we can easily understand where the magnetic field comes from, similar to the electric field. And It's true that it's not something that's very common in the sense that we don't usually do calculations. We don't usually do lots of calculations that involve the magnetic potential. But when you want to study quantum effects, quantum properties, then you need to take into account this magnetic field. It's subtle, but it's there, and it's important to understand it and know it and know that it's there. Okay, so hope you find this interesting. Maybe you were one of those that didn't realize that this subtle quantity is actually always present, and then now you know it. Okay, so let me know about your opinions in the comments, and see you to talk about another interesting topic.